Hello and welcome. In Docker Part 1 course, we begin with Chapter 1, where you will learn what Docker is, how it helps in real projects, how to install it, and how to run your very first containers. You will also understand key concepts like the difference between images and containers, and how to run an interactive container. In Chapter 2, we focus on the core commands you will use daily, working with images, checking logs, and jumping inside containers. Chapter 3 covers building your own images using Docker files, building and tagging them, pushing them to Docker Hub, and understanding caching and layers. Chapter 4 explains data persistence with volumes, the difference between bind mounts and named volumes, and running databases with persistent data. Finally, Chapter 5 introduces networking and ports, where you learn port mapping, container-to-container networking, and connecting a web app container to a database container. Install Docker and verify. Before we can use Docker, we need to install it. On Windows or Mac, the easiest way is to download Docker Desktop from the official Docker website. On Linux, you can install Docker Engine using your package manager. After installing, we need to make sure Docker is working. To do this, open a terminal if you are on Linux or Mac. If you are on Windows, open PowerShell. This is the place where we will type Docker commands. The first command to test is docker -- version. This will show the Docker version number that is installed on your system. The second command is docker info. This will print a list of system details, such as the number of containers, the number of images, and which storage driver Docker is using. If both commands give valid output, it means Docker is installed correctly and ready to use. Run your first container. Now that Docker is installed, let's run our very first container. Open your terminal on Linux or Mac, or PowerShell on Windows. Type the command docker run hello-world. Here is what happens step by step. Docker will first check if the image called hello-world is available locally. If it is not, Docker will automatically download it from Docker Hub, which is the public image registry. After the download, Docker starts a container from that image. The container will immediately run a small program that prints a friendly success message. If you see the message, it means Docker can pull images, create containers, and run them successfully on your system. This is the classic first test, just like printing Hello World when learning a new programming language. Key concepts. Image. Before we continue running commands, we need to understand two very important terms in Docker: image and container. Let's start with image. An image is like a blueprint or a template. It is read-only, which means it cannot be changed while running. An image contains everything needed to run a program. That includes the application code, libraries, system tools, and other dependencies. For example, you can download an image of Ubuntu Linux or an image with Python pre-installed. These images act as building blocks. Remember, an image itself does not run. It is just the recipe. Key concepts. Container. Now let's talk about container. A container is the running instance of an image. If the image is the blueprint, then the container is the actual house built from that blueprint. When you run an image, Docker creates a container. Containers are lightweight and isolated, which means they don't affect your main operating system. You can start them, stop them, or delete them whenever you like. For example, if you run the Ubuntu image, Docker will start a container that behaves like a tiny Ubuntu operating system inside your computer. So, to summarize, an image is the template. A container is the live, running object created from that template. Run an interactive container. Now let's try something more exciting. We will run a container in interactive mode. When you normally start a container, it may run a program and stop immediately. But sometimes, we want to go inside the container and interact with it like a small virtual machine. For this, we use two special options, -I and -T. The -I option keeps the input open. The -T option attaches a terminal so you can type commands together. We write them as -IT. The command is docker run -IT ubuntu bash. This will download the Ubuntu image if you don't already have it. Then it will start a container and give you a bash shell prompt inside it. From here, you can type normal Linux commands such as ls to list files or pwd to print the current directory. When you are finished, type exit to close the shell and stop the container. Let's review what we learned in Chapter 1. First, we installed Docker and confirmed the installation using docker-version and docker info. Next, we ran our very first container with docker run hello-world. This proved that Docker can download an image, create a container, and run it successfully. Then we learned the difference between image and container. Remember, an image is the blueprint, and a container is the running instance created from that blueprint. Finally, we explored interactive mode using docker run -IT ubuntu bash. This allowed us to enter a container and run Linux commands inside it. At this point, you have reached the goal of Chapter 1. You now know how to start and stop containers, and you understand the key difference between images and containers. Docker PS, Docker stop, Docker RM. Now let's learn the core commands you will use every day with Docker. The first command is Docker PS. This shows all containers that are currently running. If you want to see every container, even the stopped ones, use Docker PS -A. Next, to stop a container, we use Docker stop followed by the container ID. And if you want to completely remove a container, the command is docker rm followed by the container ID. Together, these commands help you list, stop, and clean up containers on your system. Docker images, Docker pull, Docker RMI. Now let's talk about managing images. The first command is Docker images. This lists all images currently stored on your computer. You will see the image name, its tag, the image ID, and size. If you want to download an image manually, use Docker pull followed by the image name. For example, Docker pull Ubuntu will fetch the latest Ubuntu image from Docker Hub. To remove an image that you no longer need, use Docker RMI followed by the image ID. Remember, you cannot remove an image if there are containers still using it. You must first delete those containers. These commands help you keep track of which images you have and manage disk space on your system. Augs and debugging. Sometimes a container starts and then exits quickly, or it runs but doesn't behave as expected. To figure out what happened, we use Docker logs. The command is Docker logs followed by the container ID or the container name. This shows everything the container has written to its standard output and error streams. If you want to watch the logs in real time, add the -F option. That means you will see new messages appear as the container is running, just like watching a live console. This is especially useful when debugging applications like web servers or databases running inside containers. We type docker run --name test-hello hello-world. Here, --name test-hello means we are giving the container a custom name. In this case, test-hello. This makes it easier to refer to the container later instead of copying its long ID. The last part, hello-world, is the image we are running. This is the same test image we used before, which prints a hello message and then exits. Next, type docker logs test-hello. Because we named the container test-hello, we can use that name instead of the container ID. The logs will show the hello message that the container printed when it ran. Finally, we can type docker logs -f test-hello. The -f option means follow. If this were a long-running application, such as a web server, you would see new log lines appear live as the container continues to run. With this command, you now have a way to look inside containers and understand what they are doing or why they exited. Jump inside a running container. Sometimes you need to look inside a running container to see what is happening. For this, we use the command docker exec-it container id bash. The word exec stands for execute. It means run a command inside an already running container. The option -i keeps the input open and -t gives us an interactive terminal. Finally, the word bash starts a shell inside the container. With this, you are literally inside the container, just like when we used docker run -it ubuntu bash earlier. But the difference is, exec works on containers that are already running. This is extremely useful for debugging. For example, if your container is running a web application and something goes wrong, you can jump inside and check the logs, files, or processes. Let's try an example. First, type docker run -d -name my -ubuntu ubuntu sleep 300. Here's what this means. -d means run in the background, also called detached mode. -name my -ubuntu gives the container a name so it's easy to use later. The image is Ubuntu. The command sleep 300 just keeps the container alive for 5 minutes, so we have time to enter it. Now, type docker exec-it my-ubuntu bash. This opens a bash shell inside the running container. Inside, you can run Linux commands such as ls, which lists files and directories, or pwd to see the current directory. When you are done, type exit. This closes the shell, but notice the container continues running in the background. This shows you how to jump inside containers to inspect and debug them without stopping them. Let's review what we learned in Chapter 2. We started with container management. Docker ps shows running containers. Docker ps space -a shows all containers, including the stopped ones. Docker stop stops a container. Docker rm removes it completely. Next, we learned how to manage images. Docker images lists all local images. Docker pull downloads a new image from Docker Hub. Docker RMI removes an image from your system. Then we explored logs. Docker logs shows what happened inside a container. Adding -f lets you follow logs in real time, which is great for debugging. Finally, we learned how to jump inside a running container with docker exec-it container id bash. This allows you to open a shell, run commands, and explore the container while it is still running. Writing a simple Dockerfile. Until now, we have only used images created by others, like Ubuntu or Hello World. But in real projects, you often need to build your own image with your code inside. To do this, we write a file called a Dockerfile. A Dockerfile is just a plain text file with a set of instructions that Docker uses to build an image. The most important commands in a Dockerfile are from sets the base image you want to start from. For example, Ubuntu, Python, or Node. Run runs a command during the image build process, like installing software or packages. Copy copies files from your computer into the image. This is how your code gets inside the container. CMD defines the default command that should run when the container starts. By combining these instructions, you can create custom images that package your application with everything it needs. Let's walk through a very simple Dockerfile for a Python application. First line, from Python:3.9. This means our base image is the official Python image version 3.9. Next line, copy app.py/app/app.py. This copies a file called app.py from our computer into the container inside a folder named app. Next line, workdir/app. This sets the working directory inside the container to /app. That means future commands will run in that folder. Last line, cmd square bracket python app.py square bracket. This tells Docker that when the container starts, it should run the command python app.py. With this short Docker file, we have packaged our Python application into a reusable image. Building images. Once you have written a Docker file, the next step is to build the image. The command is docker build-t myapp. Let's break it down. Docker build tells Docker to create a new image based on the instructions in the Docker file. The option -t myapp gives the image a tag or name. In this case, we call it myapp. You can choose any name you like. The dot at the end represents the current directory. Docker will look for the Docker file in that directory and use it to build the image. When you run this command, Docker will process each line of the Docker file step by step. It may download the base image, copy your files, and prepare everything into a final image. After the build completes, you will see your new image listed when you run Docker images. Tagging and pushing to Docker Hub. So far, we built our own image called myapp. But what if we want to share it with others or use it on another machine? That's where Docker Hub comes in. Docker Hub is a public image registry where anyone can store and download images. The process to upload your image has 3 steps. Step 1. Log in. Run Docker login and enter your Docker Hub username and password. Step 2. Tag your image. Use Docker tag myapp username /myapp:1.0. Here, replace username with your actual Docker Hub username. This creates a new name for your image that includes your account name and a version tag, in this case 1.0. Step 3. Push your image. Run docker push username /myapp:1.0. This uploads the image to your Docker Hub account. After that, anyone can pull and run your image from Docker Hub, including yourself on other machines. Image layers. When Docker builds an image, it doesn't create one big block. Instead, it builds the image in layers. Each instruction in your Docker file creates a new layer. For example, the from command creates the base layer, a run command creates another layer, a copy command creates yet another layer. These layers are stacked on top of each other to form the final image. The advantage is that Docker can reuse layers between builds and between images. Also, remember that layers are read-only. Once created, they don't change. When a container runs, Docker adds a thin writable layer on top of the image layers so the container can create or change files. Understanding layers is important because it explains why builds sometimes feel slow and why Docker caching helps. Caching and rebuilds. Now let's talk about caching. When you build an image, Docker saves each layer in a cache. If you run the same build again and nothing has changed in that step, Docker will reuse the cached layer instead of rebuilding it. This makes rebuilds much faster. But here is the catch. If one instruction changes, Docker must rebuild that layer and all the layers that come after it. For example, if you move a copy command higher up in your Docker file, every rebuild will copy the files again and rebuild all the later steps, even if nothing else has changed. A common tip is to place instructions that don't change often, like run app-get install before the copy command. That way, installing dependencies can be cached, and only your code changes will trigger rebuilds. This understanding can save a lot of time when working with large projects. Let's quickly review what we learned in this chapter. First, we saw that a Dockerfile is like a recipe that tells Docker how to build an image. Some key instructions are from to choose the base image, run to install software or run commands, copy to bring your code files inside the image, and cmd to define the default command when the container starts. We learned how to build the image using docker build-t myapp. And how to share it by tagging and pushing it to Docker Hub. Then we looked at how images are made of multiple layers. Each line in the Docker file adds a new layer. Finally, we explained caching. If a layer hasn't changed, Docker reuses it to make builds much faster. Volumes. So far, we've run containers, stopped them, and even built our own images. But here's a problem. Containers are temporary. If you start a container, create some files inside it, and then stop or delete that container, all the files will be gone. This is dangerous if you want to keep things like a database or uploaded files. That's why Docker gives us volumes. A volume is a way to store data outside of the container so it stays safe even if the container is removed. There are two main types of volumes. Named volumes, created and managed by Docker. Bind mounts. These link a folder from your computer into the container. To create a named volume, we use Docker volume create my data. Then, when we run a container, we can attach that volume using docker run-v my data:/data image name. This means mount the volume called my data into the container at the folder/data. From now on, anything saved in /data inside the container will stay in the volume, even if the container is deleted. Here's a simple demonstration. Step 1. Create a volume with Docker volume create my data. Step 2. Run an Ubuntu container with Docker run-it-v my data:/data Ubuntu bash. This mounts the volume into the container at /data. Inside the container, type echo hello volume greater than /data/test.txt. That writes the words hello volume into a file inside the volume. Now exit the container. Run another Ubuntu container, again with -v my data:/data. When you type cat/data/test.txt, you will still see the message hello volume. This proves the data was not lost. When the first container was removed, it stayed safe in the volume. Bind mounts versus named volumes. We just saw how volumes help us keep data safe even when containers stop. Now, let's compare the two main types, named volumes and bind mounts. First, named volumes. These are created and managed entirely by Docker. They live inside Docker's own storage area, usually hidden away on your computer. Named volumes are a great choice when you want Docker to handle storage for you, especially for databases or application data. Example, -v my data:/data. Next, bind mounts. Bind mounts directly map a folder from your computer into the container. This means any file changes you make on your computer will immediately appear inside the container, and vice versa. Bind mounts are especially useful during development because you can edit code on your machine and instantly test it inside the container. Example, -v/home/user/project:/app. So, the rule of thumb is, use named volumes when you want Docker to manage data storage. Use bind mounts when you need direct access to files on your computer, often while coding. Database with data persistence. Databases are one of the most common real-world use cases for volumes. Imagine running a database like PostgreSQL or MySQL inside a container. If you do not use a volume, the database files will only exist inside that container. The moment you stop or delete the container, all your tables and data will be gone. That would be a disaster in real life. The solution is to use a volume. By attaching a volume to the database's data folder, You make sure all information is stored safely outside the container. Even if the container is deleted, the volume keeps the database files. Here is an example for PostgreSQL. Here -d means run in detached mode in the background. --name mydb gives the container the name mydb. -e postgres underscore password equals secret sets the database password to secret. -v mydata :/lib/postgresql/data attaches the volume mydata to the database's data folder. And Postgres is the image we are running. With this setup, the database will keep its data safe in the volume mydata, even if the container is removed. Connect to the database inside the container with docker exec -it mydb psql-u Postgres. This gives you the PostgreSQL command line. From here, you can create tables, insert data, and all of it will be stored safely in the volume mydata. Even if you stop and remove the container, your database data will still be there. Let's quickly review Chapter 4. First, we learned that containers are temporary. If you create files inside a container and then stop or remove it, those files will be lost. To solve this, Docker gives us volumes. Volumes store data outside the container so it can survive, even if the container is deleted. We saw two types of volumes: named volumes, which are managed by Docker in its own storage; bind mounts, which directly connect a folder on your computer to a folder inside the container. A very important real-world use case is databases like PostgreSQL or MySQL. Databases must keep data safe, so we always use volumes to persist their data. Finally, we saw that the -v option is used when attaching a volume or a bind mount to a container. Now you know how to make sure your data is safe when working with Docker containers. Port mapping. By default, containers are isolated. That means if you run a web server inside a container, your computer cannot reach it directly. To make a container's service accessible from outside, we need to map ports. We do this with the -p option. The syntax is -p host port : container port. The first number is the host port. That's the port on your computer. The second number is the container port. That's the port the app is listening to inside the container. For example, Docker run -p 8080:80 Nginx. This runs an Nginx web server. Inside the container, Nginx listens on port 80. By mapping port 8080 on your computer to port 80 in the container, you can now open a browser and visit http://localhost:8080 to see the Nginx welcome page. This is how we expose container services to the outside world. Container-to-container networking. Sometimes one container needs to talk to another. For example, a web application container might need to connect to a database container. By default, Docker provides a bridge network, which allows containers to communicate. But for real projects, it's better to create a custom network because containers can then discover each other by name, making things easier to manage. To create a network, run Docker network create mynet. Now you can start containers and attach them to this network using the option --network equals mynet. When containers are on the same network, they can reach each other by their container name without needing IP addresses. For example, if you run one container named web and another named DB, the web container can connect to the database by simply using the hostname DB. This makes container-to-container communication simple and reliable. Let's check an example. Step 1. Create a network with Docker network create mynet. This makes a custom network called mynet, where containers can talk to each other. Step 2. Run a database container. Type docker run -d -name db -network equals mynet postgres. Here we are starting a container named DB using the Postgres image. Postgres is a popular open-source database. Because we attached it to the MyNet network, other containers on the same network can connect to it. Step 3. Run a web server container. Type docker run -d --name web -network equals MyNet nginx. This starts another container named web using the nginx image. Nginx is a very common web server that serves websites and web applications. It's also attached to the MyNet network. Now let's test if they can talk to each other. Type docker exec-it web ping db. This runs the command ping inside the web container. Ping is a basic tool that checks if one computer, or in this case, one container, can reach another over the network. Since both containers are on the same Docker network, the web container can find the DB container by its name. You should see successful replies, which proves the containers are connected. Web app plus database connection. In real-world applications, you rarely run just one container. For example, a web app usually needs both a web server and a database. With Docker, we can connect these containers using a custom network. Here's a simple example. We run a Postgres container, which provides the database. We run an nginx container, which provides the web server. Both containers are attached to the same custom network. Inside that network, the web container can reach the database by using its name, DB. This setup demonstrates how containers can work together as building blocks for a complete application. Let's walk through another example for networks step by step. Step 1. Create the network with Docker network create MyNet. Step 2. Run the database container. Type docker run -d -name db -network equals MyNet -e postgres _password equals secret postgres. This runs Postgres, which is an open source database. The option -e postgres _password equals secret sets the database password. The container is named DB and is attached to the network MyNet. Step 3. Run the web container. Type docker run -d -name web -network equals MyNet nginx. This starts nginx, which is a very popular web server. It's named web and is also connected to the MyNet network. Step 4. Test the connection. Run docker exec-it web ping db. Here we're running the ping command inside the web container to check if it can reach the container named DB. You should see replies, which means the two containers are communicating successfully. This is the foundation of running multi-container apps in Docker. A web app container can talk to a database container, just like in real jobs. Let's review what we learned in Chapter 5. First, containers are isolated by default. That means no outside access unless we allow it. We saw how to use port mapping with the -p option. This makes container services, like web servers, accessible from our computer through a specific port. Next, we learned about custom networks. By creating a Docker network and running containers inside it, they can talk to each other. The nice part is, containers on the same network can discover each other just by using their names, instead of complicated IP addresses. Finally, we looked at a real-world example, a web app container working together with a database container. This is exactly how real applications are built, multiple containers cooperating to provide a complete system. That's the essence of Docker networking.
Thanks for watching.